The most natural place to begin our journey into number is with the numbers we've always counted on, the natural numbers. 1, 2, 3, 4, and so on. In this lecture, we celebrate the main characters of our story and foreshadow the methods by which we'll uncover and establish the truth of theorems. Of course, there are many, in fact infinitely many, natural numbers, and making that reality intuitive, even today, is much more challenging than it first appears. As we'll soon realize, most numbers, for example, cannot even be named. But can all numbers be understood either in practice or in theory? Here we'll highlight the remarkable reality that mathematical thinking allows us to verify truths about all numbers, the unending collection of values, most of which we'll never name, imagine, or even comprehend. This reality will underscore the power of rigorous proof. Once we introduce the main characters of this course, we can turn to the means by which we can study their personalities. These traits arise through the introduction of arithmetic. It is the marriage of number and arithmetic that gives birth to the notions of number theory. We'll close this lecture with some basic but striking arithmetical observations. Some we'll see are provable theorems, while others remain hidden within a veil of mystery. Well, let's begin by recalling the different types of numbers that will follow us through our course. So we have the natural numbers, the numbers 1, 2, 3, 4, and so on. The integers consist of the natural numbers together with their negatives and also 0. The rational numbers are all ratios of integers. Specifically, a rational number is a number that can be expressed as a over b, in which a is an integer and b is some natural number. So, for instance, 2/3, 5/2, -7/8 are all examples of rational numbers. The real numbers are the decimal numbers that we're used to seeing on our calculators and computers. In other words, the numbers that correspond to points on the real number line. This course is a study involving the structure of numbers. So before we even begin, we have to ask a fundamental question about the numbers themselves. Do large numbers have any intuitive meaning to us? Clearly, there are infinitely many natural numbers, and our goal in number theory is to attain a deep understanding of these objects. The desire to understand an infinite collection of objects in a finite amount of time is the fundamental feature that makes this inquiry both subtle and abstract, and thus alluring. From a practical point of view, our understanding of numbers is dictated by their utility in our everyday lives. In fact, some early cultures actually counted 1, 2, many, because that's all they needed. Of course, today, we throw around words like millions, trillions, and barely even blink an eye. As number theory enthusiasts, we wish to study all the natural numbers. So naming them one by one becomes an issue. Even silly names can be useful, such as Google and Googleplex, the origins of which, by the way, are actually amusing stories. A Google is defined to be 10 raised to the 100 power. What does that mean? It's the number 1 followed by 100 zeros. And it was the 20th century American mathematician Edward Kasner who introduced this word around 1938. Now, as the legend goes, Kasner asked his nephew, whose name was Milton, who was about 8 years old at the time, what name he would give to a really huge number. And young Milton answered, Google. Later, Kasner defined a Googleplex to equal 10 raised to the googol power. That is 1 followed by a googol number of zeros. Well, these words have captured the public's imagination, and they're often used in referring to extremely large quantities. Well, even though a googolplex is dramatically large, the reality remains that there are infinitely many numbers, and thus, most of them, from the point of view of language, have not been named. They are unnamed. Even in our everyday world, around us, we see extremely large quantities. Scientists, for example, estimate that the number of atoms in our universe is approximately 10 to the 79th power. That's a 1 followed by 79 zeros, a very large number indeed. In mathematics, there's a ridiculously large number known as Skews number that had the folklore distinction of being the largest number that appeared in a serious theorem. Skews number equals, get ready for this, 10 raised to the power 10 to the 10 to the 34th. That's a 1 with a lot of zeros after it. And we'll actually describe the theorem that contains it in Lecture 9. Well, while these numbers are so large that they have really no intuitive meaning to us, such sizes are really insignificant from a number theory perspective, because there are infinitely many numbers greater than these relatively tiny values. In the scheme of things, when we get to even a googolplex, we haven't made much progress in our list of numbers because infinitely many natural numbers still remain to be accounted for. So we basically made no progress, even with these enormous numbers. Here, in this field of inquiry, we study those objects, most of which, in practice, we'll never see, numbers whose names we'll never utter, and yet we'll prove mathematical truths about these unnamed numbers. In this course, we'll be making discoveries about endless lists of numbers, we'll be making conjectures, and we'll strive to show that those assertions are indeed valid for all numbers. Now, we can't simply just check each natural number to verify a conjecture, since that would require us to perform literally infinitely many tasks. Instead, we rely on logical and abstract thinking and craft a rigorous proof that establishes the assertions for all numbers in general. So, where do these conjectures come from? As we suggested in the first lecture, number theorists explore numbers and search for interesting patterns. And we'll do this throughout our course. We'll constantly be looking for interesting patterns. Those patterns often lead to important insights into the structure of numbers. In fact, the great 20th century British analytic number theorist G.H. Hardy once wrote, "A mathematician, like a painter or a poet, is a maker of patterns. If his patterns are more permanent than theirs, it is because they are made with ideas." Well, you can see here that Hardy seems to be putting a hierarchical structure, putting number theory and mathematics perhaps above the painters and the poets. I don't know if I necessarily agree with that, but we do share this common creative thread, namely, we are searching for and trying to create patterns. Well, for example, let's just consider the following list of numbers that I'm going to give you, and let's see what we see. So here's the list of numbers that I'm thinking about. 1, 4, 9, 16. Let's just stop there. Now, if we look at that list of numbers, we see that they're all natural numbers and they're getting larger. Those are patterns that we observe. But what else can we say? Well, upon closer inspection, we see that each number is in fact a perfect square. That means that each number is actually some natural number multiplied by itself. Notice that 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. 16 is actually 4 squared. So in fact, there's a pattern hidden in this list of numbers. And notice that this pattern, in fact, involves products of smaller numbers, namely products of numbers with themselves. Well, this example involving multiplication brings us to the most central and important notion in number theory, that of divisibility. For example, if a number is evenly divisible by 2, then we know that it's an even number. If a number is not divisible by 2, then we automatically know it's an odd number. In other words, it's an even number plus 1. So you can see how divisibility really allows us to see something about the number. In fact, one important means of detecting the personality, if you will, of natural numbers is to factor them. That is, to write the number as a product of smaller numbers. Now, those smaller natural numbers are called factors. And sometimes the factors of a number are also known as the divisors of the number. Well, let's see these ideas in action. Let's suppose we consider one more than the product of 2 consecutive even natural numbers. Our first reaction, because there's a lot of stuff, a lot of ideas to parse. So let's try to ground our thinking. We always ground our thinking by looking at a few examples. And through the examples, we might in fact see pattern. So we're looking for 2 consecutive even numbers. That means 2 even numbers that are as close together as possible. The smallest such example would be 2 and 4. Those are 2 natural numbers that are even and as close as possible because they're sandwiching the one number 3 in between. So 2 and 4 are consecutive even numbers. We're to multiply them together, and then the rule we're told to do is to then add 1. So we're looking at 2 times 4 plus 1, which notice equals 8 plus 1, or 9. Let's try another example. Let's take a look at the next pair of consecutive even numbers. They would be 4 and 6. So I would multiply 4 times 6 and then add 1. Well, that would give us 24 plus 1 is 25. Okay, if we take a look at one final example, let's take a look at the next pair of consecutive even numbers. That would be 6 and 8. 6 times 8 plus 1 would be 48 plus 1, which equals 49. Now let's look at the answers. We see 9, we see 25, we see 49. Well, what do we see? Surprisingly, we find structure. The answer always seems to be a perfect square. Notice that 9 is equal to 3 squared. 25 is equal to 5 squared. 49 is equal to 7 squared. It's almost like magic. In fact, the number that we square seems always to be the odd number right between the 2 consecutive even numbers with which we started. 3 is between 2 and 4, for example. 5 is between the 4 and 6, and 7 is between the 6 and 8. Remarkable. Well, this evidence leads us to create a conjecture. And so here's the conjecture we would create based on this evidence. Whenever 1 is added to the product of 2 consecutive even numbers, the answer is a perfect square. In fact, the answer is the square of the odd number between those 2 even numbers. Well, there's our conjecture. And now the question is, how can we prove that this pattern holds for all pairs of consecutive even numbers? It's not enough to just check a couple. We want to prove this is true in general. Well, we'll first inspire a way of thinking about the argument by considering the issue visually. And thinking about it visually is actually important because it illustrates a wonderful life lesson that number theory teaches us. Whenever possible, we should try to look at issues from several points of view. Quite often, the vantage point we initially take on an issue might not be the one that's most efficient, most effective to allow us to build insight. Sometimes thinking about it differently allows us to actually see structure that we otherwise would miss. So before going into the details of this mathematical rigorous proof, let's see why we should believe this remarkable theorem, this remarkable conjecture. It's not a theorem yet, and see why this should make some sense. So I thought we'd try an experiment. We take a look at 2 consecutive even numbers visually. I'm going to look at 4 and 6. So 4 and 6. I'm going to represent the numbers by blocks. And this is not so easy to do, but look, I'm going to actually show it to you live. And I've arranged them so you can see that what we have here is 6 blocks against the top, 1, 2, 3, 4, 5, 6. And then down here, I see 1, 2, 3, 4. So you can see that I have 6 blocks in this row going across and 4 blocks going down. Now, what we're supposed to do is consider the product of 4 times 6, and then we're supposed to add 1. Okay, so where's the 1? Well, here's the 1. Don't think I forgot. There's the 1 that we have to add. Now, somehow, when we add 4 times 6 plus 1, we're supposed to get a perfect square. Well, what would that mean? Well, multiplying 4 by 6, you may recall, would be represented by looking at the area of this rectangle, or alternatively, how many blocks there are here. The number of blocks in this 4 by 6 rectangle actually equals the number 4 times 6. So, how can I turn this configuration into a perfect square? Well, let's watch and see what happens if we think about this together. I'm going to remove this column right here. Now, when I remove this column, what happens? I'm just going to lift it up so it's out of the way and we can look at it. Now I'm going to have 5 across since I removed 1 of the 6. 1, 2, 3, 4, 5. But notice I still have 4. 1, 2, 3, 4 down here. Now I take this and I put it on its side, like so. And if I put it down, it fits right on top. So now notice I have 1, 2, 3, 4, 5, one more than I had before. And here I have 1, 2, 3, 4, but there's a little hole, a hole for 1 cube. And notice that's the plus 1. When I put this in, almost like magic, what do I see? I see a 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. I see a 5 by 5 square. So therefore, how many cubes are there? 5 times 5, or 5 squared. 25. Well, this idea actually is the idea behind the proof of the theorem in general. If I have one even number, and then the next consecutive even number on top like this, if I were to always take up this last row and twist it up here like this, it would always fit on top with 1 extra space left over. I fill that space in, and I see a perfect square. So this shows us that, in fact, visually, this idea makes some sense. Well, let's see if we can now prove this in earnest. So capturing this idea algebraically is what we now want to do. Well, we have 2 consecutive even numbers, but we don't know what those numbers are since we're trying to prove this for every single pair of consecutive even numbers. So we give them names, but we give them names where, in fact, those names could genuinely be anything. So here's the first place that we're going to introduce some unknowns. I'm going to call the first even number 2n. So the n is any natural number at all. Notice that when I multiply by 2, it will definitely be an even number. So that represents a generic even number. Well, if we have 2n, what would be the next consecutive even number? I wouldn't add 1, I would have to add 2. I'd have to hop over that next odd number. So the next even number would be 2n plus 2. So 2n and 2n plus 2 actually represent a generic pair of consecutive even numbers. So we have to multiply them together, and then we have to add 1. So first let's multiply them together. Now we can do that using the distributive property of multiplication, and I'll do it for you. So we're going to get a little technical here. So we have 2n multiplied by the quantity 2n plus 2. When I distribute, I see 2n multiplied by 2n plus 2n multiplied by 2. Well, 2n times 2n is 4n squared, and 2n times 2 is 4n. So I'm left with 4n squared plus 4n. Now, to produce the number that we wish to study, we have to add on that 1. So I see 4n squared plus 4n plus 1. It's a mouthful. It's an algebraic mouthful, but we're done. Now, what do we want, what do we hope that that's going to actually equal? Well, we want to prove that this quantity equals the square of the odd number that's between those 2 evens. In other words, what's that odd number? It would be 2n plus 1, and I want to consider 2n plus 1 squared. Now, to square this quantity, we actually have to use the distributive property twice. So it's going to get a little bit tricky, but I'll do it for you. We have the quantity 2n plus 1 multiplied by the quantity 2n plus 1. So when we distribute the first time, I see 2n plus 1 all multiplied by 2n plus 2n plus 1 multiplied by the number 1. Now we have to distribute yet again, and I would see 2n times 2n plus 2n plus another 2n plus 1. Now when we simplify the 2n times 2n, we see 4n squared, and 2n plus 2n is actually 4n, and then I have a plus 1, which notice is indeed equal to what we found previously. So we see that 1 plus the sum of two consecutive even numbers, is exactly the square of the number that's in between. So we've just shown that our conjecture holds in general. We proved it for every single pair of consecutive even natural numbers, since we never specified which ones we were looking at. Now, actually, we could find a similar pattern with 1 plus the product of two consecutive odd numbers. For example, if we look at the first two odd numbers that are consecutive, 1 and 3, if we multiply 1 times 3, we get 3 plus 1 is 4. And notice that's actually a perfect square. And it actually happens to be the perfect square of 2 squared, which is between 1 and 3. So we seem to be seeing the exact same pattern, and I'll let you have the fun of making up your own conjecture and finding your own proof. But congratulations to us for actually coming up with our first conjecture and actually devising our first proof. Well, there's another elementary question involving even and odd numbers that's easy to state, and I want to share it with you right now. It's one of the most famous questions from elementary number theory, and it's called the 3n plus 1 question. Now, we begin with a process that generates a list of numbers. And to start, we're given a natural number, and we'll call it n, since we don't know, in fact, what we're starting with, and we don't want to specify it. And now we have two choices. If n is an even number, then the next number on our list that we're generating will be half of n, or n over 2. If n is an odd number, then the next natural number on our list will be 3n plus 1. So if n is even, then the next number will actually be smaller, half of n. If n is odd, then the next number will actually be larger. We multiply the number by 3 and add 1. Well, we now apply the same exact process with our new number to produce the next number on our list, and we repeat this process. Now, this sequence was first studied by Lothar Kollnitz in 1937. Now, as always, of course, such processes do not make any sense to us and really have no meaning until we consider examples. So let's consider some. If we start with a 1 as our first number, then what do we see? Well, 1 is an odd number, so what's the rule? We multiply by 3 and add 1 to get the next one. 3 times 1 is 3, plus 1 is 4. So our next number is 4. So we see a 1 and then a 4. Now that number 4 is actually even, so that means we take half of it. So the next number would be then half of that, which is 2. 2 still is even, so we take half of it and we see 1. Well, 1 we've already seen. We know what to do. We multiply by 3 and add 1 and we get 4. 4, we take half of it, we get 2. Take half of it, we get 1. And the pattern is clear. In fact, let's notice that a more general property actually holds. If at any point we generate the number 1, then we know that the rest of the list will just repeat. 1, 4, 2, 1, 4, 2, 1, 4, 2, and so on, forever. Now, what if we start with a 2? Well, then we see that if we start with a 2, it's even, so I take half of it. That gives me a 1. 1 is odd, so I multiply by 3 and add 1. That gives me 4, and I'm right back where I started from. So again, we see that this list is going to end with 1, 4, 2, 1, 4, 2, and so forth forever. What if we start with a 3? Okay, now this is generally going to be new. Start with a 3, that's odd, so the next number will be 3 times 3 plus 1, which is 10. 10 is even, so I take half of it to get the next number, which would be 5. 5 is odd, so I multiply by 3 and add 1. That's 15 plus 1, which is 16. 16 is even. Take half of it. 8. 8 is even. Take half of it. 4. 4 is even. Take half of it. 2. 2 is even. Take half of it. 1. Once we hit 1, we know, we've already seen, we get a 4, a 2, a 1, 4, 2, 1, and so forth forever. Interesting. Let's start with a 4. Well, that's actually easy. If we start with a 4, we take half of it and get 2. Take half of 2, we get 1. And then automatically we cycle back 4, 2, 1, 4, 2, 1, 4, 2, 1 forever. Okay, are you seeing the pattern? Let's try one last example. Let's start with 11. Okay, really different. Now 11 is odd. So we start off by multiplying by 3, that's 33, and adding 1, that's 34. 34 is even, so I take half of it, which is 17. 17 is odd, so I multiply it by 3 and add 1 and get 52. 52 is even, so I take half of it. The next number is 26. 26 is still even, so I take half of it, I get 13. Now 13 is odd, so I multiply that by 3, get 39, and add 1, which is 40. 40 is even, the next number would be half of it, 20. 20 is even, half of it, 10. 10 is even, half of it, 5. Now, 5 we've actually already seen. What do we do? After 5 comes 16, then 8, 4, 2, 1, 4, 2, 1, 4, 2, 1, and so forth. Yet again, we see a tail of an endless repeated run of 1, 4, 2, 1, 4, 2. Absolutely amazing. Notice how the numbers in the list go up and down in size. In fact, sometimes these sequences are actually called the hailstone sequences because, as many of you might know, hailstones are formed at high clouds when a small particle gets coated with layers of ice and then moves up and down in the high clouds until it becomes so heavy that it actually falls to Earth. And we're seeing that kind of pattern here wiggling. Our experimentation seems to be leading us to a conjecture. It appears that no matter what natural number we start with, the list always eventually becomes the endless run of 1, 4, 2, 1, 4, 2, and so forth. If we start with the relatively modest number, such as 27, and you can try this if you want, but I don't actually suggest it, the process will produce a list of 111 numbers before we finally come to our first one. And within those first 111 numbers, the numbers we'd see would actually go as large as 9,232. So huge. But we do finally settle down to the familiar 1, 4, 2, 1, 4, 2, and so forth. Well, mathematicians and computer scientists have actually tested every natural number up to around 3 times 10 to the 18th. That's the number 3 followed by 18 zeros. And when you start with all of these values up to that point as a starting value, in each case, the list finally does settle down into the familiar 1, 4, 2, 1, 4, 2, and so forth. Collatz himself conjectured that starting with any natural number, the list will eventually settle down to the familiar 1, 4, 2, 1, 4, 2 that we've seen. But no one has been able to prove this conjecture in general. The Collatz conjecture remains one of the most famous open questions in elementary number theory. The great 20th century Hungarian mathematician Paul Erdős, who we'll talk about in Lecture 9, actually offered a $500 prize for solving this problem. And he once wrote, "Mathematics is not ready for such problems," meaning that we don't even have the machinery to allow us to make sense of these things. So questions, even that sound simple, remain notoriously hard and difficult. Well, I want to close our lecture here by considering one last observation about the most even numbers around, the powers of 2. Well, let's just produce the first few powers of 2. 2 to the first power is just 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16. 2 to the fifth is 32. 2 to the sixth is 64. If you go out a little bit, 2 to the ninth is 512. And if you really zip up, you can get to 2 to the 24th, which is 16,777,216. Now, as you look at these screeds of digits that we have here, making up the powers, I want us to consider the following question. What are the first, meaning the leftmost digits that we see in the previous numbers? Well, what are those first digits in the powers of 2? We saw 2, 4, 8, a 1, a 3, a 6, and then later a 5. The only digits missing from our list, in fact, were just 7 and 9. Kind of interesting. Well, are there powers of 2 that begin with the missing non-zero digits 7 and 9? Well, using a computer, in fact, one can verify that 2 to the 46th power equals 70,368,744,177,664, but it starts, notice, with a 7. And 2 to the 53rd power actually is a 16-digit number that begins 9, 0, 0, 7, and so on. So what we see here is that there are powers that begin with every single digit from 1 to 9, appearing in the very first leftmost spot of a power of 2. Well, is there a power of 2 that begins with a 10, or with an 11, or with a 12? Well, is there a power of 2 that begins with your Social Security number? How about your Social Security number immediately followed by your birth date, followed by your cell phone number, including its area code? That's a really big natural number. Here's the surprising fact. As amazing as it might first seem, there is a theorem that asserts that given any natural number n at all, there exists a power of 2 whose leftmost digits agree with the digits of the given natural number n. The truly amazing aspect of this assertion is that this result can be proved for all natural numbers. The proof of this theorem actually requires many different ideas from number theory that we ourselves will explore throughout our journey together. In fact, to prove the result, we must actually leave the comfortable world of the natural numbers and apply results involving irrational numbers, which we haven't even talked about yet. This connection will be our final illustration of the incredible synergy between the many different types of numbers. So for now, I leave this whole realm of elementary questions, and I leave with the reasoning that establishes this theorem as a number theory cliffhanger that will be resolved at the very close of this course.